Good day, I hope you are doing well. My name is Janice Garcia. In this work, I discuss the correlation of temperature and time in calcination and the molarity of the silver precursor with the crystalline size of the silver nanoparticles nanomaterial. Due the fracture caused in nature by the abuse that humans have inflicted, it is our responsibility as the species accountable for most of the damage to help restore balance. This work is focused on environmental remediation, which presents a major challenge due to the complexity of populations and their interaction with ecosystems. It is now that nanomaterials are a promising alternative for the removal of contaminants. For this reason, a nanomaterial was developed using coffee waste, silver nanoparticles, and natural soil nanoparticles for water purification. The experimental methodology begins with the mixture of coffee waste and treated soil. Ethanol and silver nitrate are added to this mixture and left for 2 hours on a heated plate with stirring to ensure homogenization. Subsequently, the mixture undergoes a thermal process for 24 hours at 160 degrees Celsius, followed by calcination, yielding a gray powder. To determine the percentage of influence between parameters and crystalline size, various experiments were conducted in which the proposed parameters, silver nitrate concentration, calcination time, and calcination temperature, were varied. Using these parameters, experiments were carried out to obtain the synthesized nanomaterials, which were characterized by X-ray diffraction, XRD. From this data, the average crystal size of the silver nanoparticles was determined from full width at half maximum, FWHM. A statistical analysis was then performed to determine the correlation between the crystalline size of the silver nanoparticles and the parameters. Silver nitrate concentration, calcination time, and calcination temperature. The correlation was calculated using the Pearson correlation method, a statistical measure that indicates the degree of linear relationship between two quantitative variables. In other words, the Pearson correlation coefficient, symbolized by the letter R, measures how much and in what direction two variables change together. The value of R is always between -1 and 1. The table explains this interpretation. The closer R is to 1, the stronger the positive correlation. When one variable increased, the other also increased in exact proportion. When R is closer to O, there is no strong linear correlation. If the value of R is closer to -1, the correlation is negative. This means that when one variable increases, the other decreases in exact proportion. Considering x as the parameter and y as the crystal size, the calculator are values for time, temperature, and molarity, where obtained are equal negative 0.6854 for temperature indicated a strong negative correlation, meaning that the temperature increased, size decreased. For time, R equal negative 0.4041, showing a moderate negative correlation. When the time increased, size tends to decrease. Lastly, molarity yielded R equal negative 0.3130, also a moderate negative correlation. When molarity increases, size tends to decrease. Finally, to determine the percentage of influence of each parameter, the R values were squared, resulting in 26.89%, explained by other parameters not analyzed, such as cooling rate, distribution in the calcination furnace, humidity, and environmental contamination during synthesis, among others. 46.98% from temperature, 16.33% from time, and 9.80% from molarity, yielding a total of 73.11% influence of the model on crystal size.